So in this video, I'm going to talk about the systems of differential equations. It's a big difference. And I'm going to do that by we're going to take a walk down memory lane a little bit, look at just some first order differential equation, and a simple one, make it a little bit more complicated based on some new assumptions, and eventually our assumptions will lead us to a system of differential equations. So we're going to take back a look at just a basic population type. When we very began this class, I think the first day we talked about just a basic differential equation where the growth rate of a population depends upon or is proportional to the size of the population. And that's the basic assumption. So we're going to look at a rabbit population. So looking at a rabbit population, and our assumption is that the growth rate of the rabbits is proportional to the population, the size of the population. So, and if we know that if that's the only assumption that we're going off of, then we can write a pretty simple differential equation. We can just say the growth rate of the rabbit population is equal to some constant times the population. So our variables in there would be P is equal to the population of rabbits. That would be a dependent variable. T would be equal to time, and K would be that's the independent variable. K would be a parameter that is the constant of proportionality. So that would change depending on the population. If we're talking about people or rabbits or deer or earthworms or whatever, that there would be a different constant. And this might even be different from rabbit population to rabbit population based on where they live or what type of rabbit it is, and so forth. So, and that's a basic differential equation that's really easy to solve. We've solved that before. We can write a slope field for it pretty easily, or draw a slope field for it. We could talk about the phase line, and anyway, we can do all kinds of stuff with it, right? So this is a really basic differential equation, and we have a very good picture of it. We've played around with it a bit. But then if you think about it for a minute, the rabbits are not that simple. They don't just grow based on, and by the way, this is called the uninhibited growth. Uninhibited growth. So in other words, if there's nothing inhibiting the growth of the rabbits, they're just going to grow exponentially. And of course, rabbits are famous for that. But then the next step, we thought, well, and the basic assumption, or the basic idea is with different equations, keep it as simple as possible. But if we have some assumptions that drive us, make things a little bit more complicated, then we got to add to the differential equation. So of course, it's not that simple with a rabbit population because they grow so fast that they can outgrow their environment, meaning they'll have so many rabbits that the population, or that they will run out of food, or they will just overgraze or whatever. So there is a limited number of resources in a certain area. So the rabbit population, there is a size of the population that's too large. So in that case, we would have a new set of assumptions. So we would say, if rabbit population is small, then same as our original assumption, growth proportional to population. So as long as it's small, it's just going to grow proportionally to the population. The bigger the population, the faster the growth rate. But then our second assumption is, if population is too large, so we get close to what we call a carrying capacity. Too large for the environment, which is the carrying capacity, the population decreases. population decreases. Okay. Oh, in other words, the growth rate is negative. So growth rate is negative. Pretty sweet, huh? So now there's just two assumptions now, and it's the first one is similar to the one we had earlier, and then there's this new one based on rabbits getting outgrown their population. So we have the same independent variable, t equals time, same dependent variable, p equals population. We have that same k, which is a parameter, which is the growth rate parameter. And now we have a new thing, and we'll call it n, a new parameter. This is what measures how we measure too large. So in the assumption we said that if the population is too large, then the population decreases, so the growth rate is negative. So n is going to measure too large, and we call that usually carrying capacity. And this will be different from, forest to forest or field or wherever rabbits live. Carrying. And this is really true for a lot of different populations. In fact, I remember when I was in high school, there was a big deal about that the Earth's people population was closing in on its carrying capacity. Like the Earth could only, and that was 40 years ago. So they were saying that, I think they were predicting in the year 2000 that we would outgrow the Earth and disaster would strike because the Earth couldn't handle this many people. Okay, so now we need a new assumption. We got a new assumption. We need a new equation. So basically what we'd have to keep in mind is that P of t, when P of t is less than the carrying capacity, it's increasing. And when P of t is greater than n, it's decreasing. So we somehow have to write a differential equation that expresses that. And so one way to do that is we write dp dt is equal to that same constant, but it can't just be p, there has to be something else in there. So we're going to multiply it times 1 minus p over n. And a lot of you guys did this in your, or some of you did it in your discussion board when you're creating your functions. This is a way to deal with, and actually on the test, a lot of people came up with this when we talked about the rhino population that was, if it got too large. So, so you can tell here that if p is 0, then this is just k times p. Of course, if p is 0, then it wouldn't be growing. But if p is a little bit more than 0, it won't be much different than this, because this will be a small number, because n is usually, some like 500 rabbits or 2,000 rabbits, depending on what the carrying capacity is. So if the population is 1, for example, we'd have 1 over 500. So this would be roughly that. But as p grows, then this is becoming less than 1. And so we're not getting the full growth capacity, because we're multiplying k times some number less than 1. And of course, when p equals n, when the population gets to the carrying capacity, we end up with 1 minus 1, which would be 0, and the population stops growing. So you can see that this kind of takes care of that issue. Now, if p was greater than n, then we'd have 1 minus a number bigger than n, so it'd be negative. We turn our k into negative, and that would make my my growth rate negative. So it takes care of the thing that we wanted it to do. This is called the logistic model. Logistic model. Because I guess it's taking into logistics that rabbits have to eat. Okay, and that was informative, and we feel like we're getting closer at the idea of how rabbits populate the earth. But of course, if you think about it for a little bit, eating food is not the only thing rabbits have to worry about. They also have to worry about being eaten. So, so there's such a thing as fox in the area. So we introduced fox. So of course, rabbits could run out of food, but they also could be eaten by fox or other predators. But we'll just, for now, to keep it simple, we'll just think about a fox. So now we're going to get a new set of parameters, and this is going to get a lot more complicated. So let's just say if no fox, if there aren't any fox in the area, or any other predators, but again, we're not thinking about the other predators yet, we're just talking about fox. So if no fox, then rabbits grow uninhibited. Uninhibited. In other words, proportional to the growth to the population, just like our first model. Okay. Second assumption, fox eat rabbit. That's an assumption that they do, and that's at a rate proportional proportional to the rate at which fox and rabbit interact. So in other words, if we have a bunch of fox and rabbit running around in a meadow or field or whatever, there's a certain percentage chance that they're going to interact. And what happens when a rabbit and fox interact? Well, the fox is probably going to eat the rabbit. Now, of course, the rabbit could get away, so there's some kind of a proportional or a constant of proportionality. So okay, so of course, well, anyway, we'll have to deal with that. Another assumption is without rabbits, the fox population decline. And that's proportional to fox population. So if there aren't any rabbits, of course the fox don't have anything to eat, or maybe they don't have enough to eat because maybe they might still be able to eat some mice or something. So their population is starting to decline because they don't have enough food to eat. Okay, and then the final, I think this is the final assumption. Yeah, rate at which fox grow is proportional to number of rabbits. So the more rabbits, because they're eating the rabbits, and so the more rabbits in the area, the more the fox population is going to grow, or the faster the fox population is grow. So now we got some new parameters. We're going to say, for example, alpha is the growth rate coefficient of rabbits. So remember that was K in the first example and the second example for that matter. We're going to let beta equal, we're going to Greek letters because we got too many of them. And that's a parameter. Oh, and we have the same independent, or we actually have a new dependent variable, but we have the same independent variable, t equals time. And we're going to let r equal rabbit population, because we have more than one population now. And we'll let f equal fox population. So R and F are dependent variables. T is independent variable. Okay, so then B is going to be the constant of proportionality. Proportionality of, let's see, that measures the number in fox and the fox and rabbit interaction of fox and rabbit interaction. So in other words, it's a constant that's going to tell us the success rate of fox eating rabbits. So if we take the number of rabbits and the number of fox, this constant is going to tell us the proportional of how that affects the fox and rabbit population, because when rabbits are eaten, that's going to cause the rabbit population to decline, and it's going to cause the fox population rate to grow. So, and then we got, I forget what these are called. Is this lambda? I think this is called a lambda. And that's going to be the death rate. Death rate coefficient. For the fox. And then we have gamma. And that's going to be the constant proportionality. That measures the benefit of fox interaction. Benefit to fox in the interaction. Yeah, I guess we need two different ones, because here this is the constant proportionality for the fox and rabbit interaction that has a negative effect on rabbits. And this is the positive effect on fox. So these two are different constants based on, this is on how the interaction between fox and rabbit affects the rabbits, and this is how the interaction between fox and rabbit affect the fox. Okay, so now that we have all this stuff defined, we're going to write now because there's so many different parameters and two different dependent variables, we can't really represent this as just one equation. So what we do is come up with a system of differential equations. So this is going to be dr dt is equal to alpha times r, because that's just the growth rate of rabbits, right? But then there's this other factor of, and remember we had a beta up here that's the negative effect of the fox and rabbit interacting. And so we're going to take the number of rabbits times the number of fox, and when they interact, bad things happen to the rabbits. And this tells us the rate at which the bad things happen. And then if we do df dt, that's going to be equal to negative lambda. I have a real hard time writing lambdas. F, and this is the death rate of the fox, right? So they are going to decline. In other words, remember we said without any rabbits, they start declining. Plus, but then we have the benefit of the rabbit-fox interaction. So you can say this is a system of differential equations. It's a first-order differential system because there's no second derivative involved, and we would say that this system of differential equations is coupled, which means kind of like what it sounds, is because both equations, oops, I spelled both wrong. Both equations depend on R and F. So the fox and rabbit population affect the growth rate of fox, and the fox and rabbit population affect the growth rate of rabbits. So there's an example of a differential equation. I think I'm gonna finish this here pretty soon, but let's just look at the differential equation a little bit. We can do some basic thoughts. Now this differential equations don't have as many. We're not going to have as much success solving them with a qualitative, actually come up with a equation for it. Some of them we will be able to, but a lot of times we'll just kind of play around with them and try to, like we did in early in the chapter with just the first equations, where we just made slope fields and phase lines and all that kind of stuff and we used Euler's method to try to estimate it. So we can do a lot of those same types of tools. Of course, they're a little bit different when they're applied to differential equations or systems of differential equations. But we'll have a much lower success rate in solving them for an actual function. But of course, if we were to solve them, we'd have to come up with an R of t and an f of t that would be, since it's a system of equations, just like when you solve a system of equations that weren't differential, just a normal equations, you had to come up with an x and a y. So a number for the x variable and a number for the y variable. So you'd never say the solution of a system of equations is 5. It'd have to be 5 and 7 or something like that. So same thing here. If I'm coming up with a solution to a system of equations, I have to come up with two functions that I could plug in. So I'd plug in r there, and there, and I'd have to plug f in all the places where you see f, and it would make both equations true. Okay, so let's talk a little bit about some solutions. Of course, we have the basic solution. If r of t is equal to 0 and f of t is equal to 0, then we have what we call an equilibrium solution, because if you plug 0 in for r and f, we end up with r, or dr dt is equal to 0, and df dt is equal to 0. And that obviously produces a solution. And this would make sense, of course, if the rabbit population was 0 and the fox population is 0, then the growth rate would be 0. Nothing would happen, right? So that's it. That's an equilibrium solution. Equilibrium. And you guys remember us doing those with just a single differential equation. We could also do this, and this one will make less sense, but of course these are not necessarily the right parameters. If we take the rabbit, the differential equation with dr dt and factor out r, and then we take the and then if we take df dt, and that's equal to, if we factor out the f, we get -1 plus 0.9 r times f. And you can see another potential equilibrium solution, where we could, let's see, if f is equal to 2 divided by 1.2, and if r, I guess I should put f of t, capital F, and if r of t is equal to 1 divided by 0.9, you can see that that would make that 0, and this would make that 0. And so once again, we'd get dr dt equals 0 and df dt equals 0, which would be another equilibrium solution. And now the basic idea, this says that if there is potentially a place where the rabbit population and the fox population would be in perfect balance, where there's enough rabbits to keep the fox alive, keep the fox growing at a nice steady level, but they're not eating so many that it's causing the the rabbit population to decline, and so there is a potentially a equilibrium solution. In this case, it would mean that the fox population stays at 2 divided by 1.2, which doesn't really make sense, but you could see that there is a potential thing there. We could also maybe look at this, what if r is equal to 0? Well, that would mean that df dt is equal to negative f, and we talked about that. If there's no rabbits, then the fox population declines. And also, what if f equals 0? Then we take dr dt, and that would be equal to 2r, and so that would be, if the fox population turns to 0 somehow, maybe they got shot or something, or hunted, or trapped or something. So then the rabbit population would go back to growing uninhibited, because there weren't the fox there to keep them in check. But then, of course, they would run into that possibly a carrying capacity. So we'd have to go back to that second model. Okay. So anyway, that's just some basic ideas about kind of coming up with a system of differential equations, and then also beginning to investigate at least the equilibrium and some basic solutions without doing any kind of a method of solving it. And we'll get into more things where we can estimate it and do something like a slope field. So hopefully this kind of whets your taste buds for more.